Here's something your teachers got wrong. Not maliciously, not carelessly, just wrong. Or at least incomplete in a way that matters. From the moment you were old enough to look at a globe, you were handed a story about the shape of the Earth. The story had a clean, satisfying arc. Flat earthers were ignorant, round earthers were enlightened, and once humanity figured out the planet was a sphere, the case was closed. Ball. Done. Move on. Except the Earth is not a sphere, not even close. And I don't mean that in some abstract, technically speaking, rounding error kind of way. I mean the Earth is genuinely, measurably, structurally weird, misshapen in ways that have enormous consequences for how gravity works, how satellites orbit, how sea level is defined, how GPS functions, and how we understand the interior of the planet itself. The shape of the Earth is one of the most actively researched problems in all of modern science, and the answers coming back are stranger than most people ever hear about. And in the last few years specifically, with satellite gravity mapping missions, advanced seismic imaging, and a new generation of geodetic measurements, we've learned things about the Earth's shape that would have seemed almost surreal to scientists even 50 years ago. The planet is lopsided. It has a dent. It has a bulge the size of a continent. It's taller on one side than the other by a measurable amount. It wobbles. It breathes, in a sense, actually changing shape over seasons. And underneath the oceans and continents, the interior of the planet is so uneven, so lumpy with variations in density, that the gravitational field it generates is a warped, asymmetric field that no textbook diagram has ever accurately shown you. We have been standing on this planet for hundreds of thousands of years. We've only just started to understand what shape it actually is. That's what this video is. We are going to take the globe, that comforting, symmetrical, perfect sphere that's been sitting on your mental shelf since childhood, and we are going to show you what the Earth actually looks like. We're going to go layer by layer, surface, then gravitational field, then interior, then the dynamic shape that changes in real time as the planet moves and breathes and wobbles through space. By the end of this, you will never look at a globe the same way. Let's start with the first correction. Chapter 1, The Myth of the Perfect Sphere. Let's talk about the globe on your desk, or the one in your head, or the one in every classroom you've ever been in. It's a sphere, a smooth, round, perfectly proportioned ball. Spin it, and it feels right. It has that satisfying completeness that a sphere has, the same geometric perfection as a soap bubble or a marble. And for most practical purposes, for most of human history, this was good enough. The ancient Greeks deduced the Earth was round from the shape of its shadow on the moon during lunar eclipses, from the way ships disappeared over the horizon hull first, from the fact that different constellations are visible at different latitudes. Eratosthenes, around 240 BC, even calculated the Earth's circumference with remarkable accuracy using the angle of shadows cast in two cities on the same day. Spherical Earth? Elegant. Confirmed. Case closed. Except by the 17th century, something started bothering astronomers and mathematicians. Isaac Newton, working out his theory of gravity and the mechanics of rotating bodies, predicted that a spinning sphere wouldn't stay a sphere. He argued that the centrifugal effect of rotation would cause any self-gravitating, rotating body to bulge at its equator and flatten at its poles. Think of it like spinning pizza dough. The rotation flings material outward from the center, and anything flexible enough will respond by becoming wider around the middle and squashed at the top and bottom. Newton's prediction was bold and specific. The Earth, he said, should be an oblate spheroid, fatter at the equator, flatter at the poles, not by a tiny amount either, by a detectable, measurable amount. He calculated the difference between the equatorial and polar radii, and the number was significant. There was a problem. The French didn't believe him. This became one of the great scientific disputes of the 17th and 18th centuries. The French Academy of Sciences had its own competing theory, that the Earth was actually a prolate spheroid, meaning it was elongated at the poles and narrowed at the equator, like an egg standing on end. The dispute wasn't trivial. It had enormous practical consequences for navigation, map-making, and understanding how gravity actually worked. To settle it, the Academy organized two extraordinary expeditions in the 1730s, one to Lapland, near the Arctic Circle, and one to Peru, near the equator, to precisely measure the length of 1 degree of latitude in each location. If Newton was right, a degree of latitude near the poles should be longer than near the equator, because the pole is flatter. You're measuring along a more gradually curving surface. If the French critics were right, the opposite would be true. The results came back. Newton was right. The Earth is an oblate spheroid, and the numbers that came out of those expeditions, refined over 3 centuries of increasingly precise measurement, are these. The Earth's equatorial radius is approximately 6,378 kilometers. The Earth's polar radius is approximately 6,357 kilometers. A difference of about 21 kilometers. Now, 21 kilometers doesn't sound like much against a planet that's nearly 13,000 kilometers across. As a fraction, it's less than half of 1%. And this is why, when we draw globes, we draw them as perfect spheres. The difference is too small to see at any normal scale. If you made a globe 1 meter in diameter, the equatorial bulge would only amount to about 3 millimeters. You couldn't see it. You'd have to measure it. But here's the thing. That 21-kilometer difference is not a rounding error. It's not a technicality. That 21-kilometer difference means that the surface of the Earth at the equator is 21 kilometers further from the center of the planet than the surface at the poles, which means Mount Everest, commonly described as the tallest mountain on Earth at 8,849 meters above sea level, is not actually the closest point on Earth's surface to outer space. That distinction belongs to a volcano in Ecuador, Chimborazo. At 6,263 meters above sea level, it's not even the tallest mountain in South America. But because it sits almost directly on the equator, it benefits from all 21 kilometers of equatorial bulge. Measure from the Earth's center, from the actual core of the planet. And Chimborazo's summit is further from that center than Everest's by about 2,168 meters. Chimborazo is the closest point on Earth's surface to outer space, not Everest. Your geography teacher probably didn't mention that, but we're only getting started, because an oblate spheroid, flat at the poles, fat at the equator, is still a beautifully regular, mathematically smooth shape. it's still a shape you can describe with a simple equation. It still has a kind of geometric dignity. The real shape of the Earth is neither smooth, nor regular, nor describable by any simple equation. It's called the geoid, and it's one of the strangest, most counterintuitive shapes in science. Chapter 2: The geoid, the true face of Earth. Here's a question nobody asks in school. What does sea level mean? We use the phrase constantly. Mountains are measured above sea level. Buildings are rated for flood risk based on elevation above sea level. Aviation operates at altitudes defined in relation to sea level. The entire global coordinate system, the GPS in your phone, the maps on your screen, is built on a reference to sea level. But what precisely is sea level? On the face of it, the answer seems obvious. Sea level is the average height of the ocean surface. Easy. Go to the beach, watch the tide, average it out, and there you have it. Except the ocean surface is not level, not even close. The ocean is not a uniform, flat surface that simply sloshes around in a big bowl. The actual ocean surface, corrected for tides, waves, and currents, is lumpy, genuinely, measurably lumpy. In some places, the ocean surface is up to 85 meters higher than in others. The North Atlantic Ocean is actually about 1 meter higher than the North Pacific Ocean. The ocean around Iceland is higher than the ocean around Australia. Why? Because the ocean isn't responding to a geometry. It's responding to gravity. And gravity is not uniform across the surface of the Earth. Gravity is stronger in some places than others. Where gravity is stronger, above a dense underground formation, above an undersea mountain range, above a thick slab of heavy rock, the ocean's surface is pulled upward, piling up slightly above the global average. Where gravity is weaker, above a region of hot, less dense mantle, above an area where a kilometer-thick ice sheet melted 10,000 years ago and the land hasn't finished rebounding, above an unusually large void in the crust, the ocean surface sits slightly lower. The ocean surface doesn't care about geometry. It sits at a constant gravitational potential. At every point, it finds the level where the pull of gravity is in equilibrium, and that level is lumpy, irregular, shaped not by mathematics, but by the uneven distribution of mass beneath the Earth's surface. Scientists call this shape the geoid. The geoid is defined precisely as the surface of equal gravitational potential that corresponds, on average, to sea level. It's the shape the ocean would take if there were no continents blocking it. If you imagined a planet-sized ocean, perfectly calm, covering the looks nothing like a sphere. It looks nothing like a sphere. It looks nothing like an oblate spheroid. It looks, and I'm not exaggerating here, like a lumpy potato. In 2011, the European Space Agency released the most precise map of the geoid ever made, based on data from a satellite mission called GOES, the Gravity Field and Steady State Ocean Circulation Explorer. GOES flew at a remarkably low orbit, just 255 kilometers above the surface, skimming through the very top of the atmosphere, so sensitive to changes in gravitational pull that it could detect the difference in gravity between one room and the next. It spent 4 years in orbit, mapping the gravitational field of the Earth to a resolution never previously achieved. The resulting geoid model, visualized as a 3-dimensional shape where the surface is elevated wherever gravity is stronger and depressed, wherever it's weaker, is extraordinary. It has a deep dent south of India. It has a pronounced bulge over New Guinea. It has regions that sit dozens of meters above or below the mean spheroid, creating what gravitational scientists describe, without embarrassment, as a potato-like or lumpy appearance. The dent south of India is particularly dramatic. In a region of the Indian Ocean south of Sri Lanka, the geoid sits roughly 106 meters below where it should be on a perfect oblate spheroid. 106 meters. In a region of ocean that looks, from a satellite photograph, perfectly ordinary, flat, blue, unremarkable, the gravitational field is so much weaker than surrounding areas that the sea surface is pulled down by the equivalent of a 10-story building's height. Nobody could explain it for decades. As recently as the 2000s and 20s, it remained one of the genuine open mysteries of geophysics. Why does gravity dip so steeply in the Indian Ocean? What is underground in that region that's so dramatically less dense than the surrounding mantle? In 2023, researchers from the Indian Institute of Science in Bengaluru published a study proposing an answer. Their modeling suggested that the Indian Ocean geoid low, as it's technically called, is the remnant of an ancient ocean floor, specifically the floor of the Tethys Sea, an ancient ocean that existed between 220 million years ago, before the Indian subcontinent collided with Asia and pushed up the Himalayas. As the Tethys Sea closed, its floor was subducted, pushed down into the Earth's mantle beneath what is now Asia. And deep in the mantle, at depths of perhaps 900 kilometers, those remnants of ancient ocean crust are still sitting there, cooler, denser, but surrounded by disturbed, roiling mantle material, creating a region where the density is just different enough, in just the right way, to pull the gravitational field downward. An ancient ocean is carving a dent in the sea, surface 20 million years after it ceased to exist. Let me say that again. The ocean floor is 106 meters lower than it should be right now today, because of a sea that closed before the Himalayas existed. The geoid is not just a map of the present. It is a fossil record of the deep past, written in gravity. But here's what makes the geoid truly paradigm-shifting and why it matters beyond just being scientifically interesting. The geoid is what we use to define zero elevation, the baseline from which every altitude on Earth is measured. Every mountain's height, every city's elevation, every floodplain's risk, every aircraft's altitude. All of these are measured relative to the geoid, not relative to the geometric center of the Earth, and not relative to any perfect mathematical surface. When you say Everest is 8,849 meters above sea level, what you're actually saying is Everest's summit is 8,849 meters above the geoid. Above the surface of equal gravitational potential, that sea level follows in that part of the world, which means the sea level being referenced at Everest's base in the Himalayas is not the actual sea. It's the imaginary surface the sea would reach if the continents didn't exist. Your altitude, right now, wherever you are, is measured against a lump-shaped, gravity-defined, geologically influenced, ancient ocean-haunted invisible surface that your GPS is quietly consulting every time it places you on the map, a lumpy potato. That's what sea level is built on. Chapter 3, the bulge that changes everything. let's go back to the equatorial bulge for a moment, because we brushed past it quickly in Chapter 1, and it deserves more attention than it got. 21 kilometers. The equatorial radius minus the polar radius. That's how much the Earth bulges outward at the equator compared to the poles. Where does that bulge come from? You already know the short answer: rotation. The Earth spins, centrifugal force pushes outward, and the planet, which is not rigid, not all the way through, and has had billions of years to settle into equilibrium, has spread outward around its waist. But the story is more interesting than that, because the equatorial bulge is not a fixed, stable feature. It changes. Not fast. Not in a way you'd notice in a human lifetime, but measurably, meaningfully, consequentially. Here's one way it changes. Water. Every year, water moves around the planet in enormous quantities. When winter arrives in the northern hemisphere and snowfall accumulates on the continents, the Siberian plain, the Canadian Shield, the Scandinavian highlands, billions of tons of water leave the oceans and pile up as ice and snow on land. In summer, it melts and returns. This seasonal redistribution of mass, billions of tons of water moving from ocean to land and back, subtly alters the Earth's rotational dynamics, and by extension, its shape. The equatorial bulge responds. When mass moves toward the poles, piling up as snow at high latitudes, the planet's moment of inertia changes slightly, and the rotation speeds up very slightly, like a spinning figure skater pulling in their arms. The bulge contracts a little. When mass moves back toward the equator in the melt season, it expands again. The Earth breathes, seasonally, in a way that changes its shape by millimeters, measurable from space. But here's the version of the story that is genuinely alarming, and that has direct, practical, civilization-scale consequences. The equatorial bulge is also responding to the melting of the polar ice caps. As the Greenland ice sheet and the West Antarctic ice sheet lose mass, and they are losing mass at an accelerating rate, with Greenland alone losing an average of about 280 billion tons of ice per year. That mass is redistributed. It leaves the poles and flows into the oceans, which are more equatorially distributed. The Earth's equatorial bulge is, as a result, slowly growing, not dramatically. We're talking about changes at the scale of millimeters per year, but those changes are measurable from space, and they have a cascade effect. As the bulge grows, the Earth's moment of inertia increases, which causes the rotation to slow slightly. The days get very, very fractionally longer. The shift in mass also changes the positions of the Earth's rotational poles. The actual geographic poles are moving as the ice melts, currently drifting toward Greenland at a rate of about 10 centimeters per year. The melting ice is moving the poles, and it's changing the shape of the planet. Not metaphorically. The actual physical shape of the oblate spheroid is changing because of climate change. Satellites can measure it. Geodesists, scientists who study the shape of the Earth, have confirmed it. The climate crisis is literally reshaping the planet. But the equatorial bulge has another effect that almost nobody knows about, and it's one of the most beautiful and practically important consequences of Earth's non-spherical shape. Satellites. When early satellite engineers in the 1950s and 1960s tried to calculate precise orbital trajectories for their spacecraft, they quickly discovered that the equations they'd been using which assumed a perfectly spherical Earth, were wrong. Not approximately wrong. Wrong enough that satellites would drift significantly off course if the engineers didn't account for the planet's actual shape. The equatorial bulge exerts a gravitational pull on satellites that's stronger on the equatorial side and weaker on the polar side. This asymmetric pull causes a phenomenon called nodal regression, a slow rotation of a satellite's orbital plane around the Earth's axis. The rate of this regression depends on the satellite's altitude and inclination. And far from being merely a nuisance, engineers quickly realized that nodal regression could be harnessed. Sun-synchronous orbits, used by most Earth observation satellites, including weather satellites and spy satellites, exploit the equatorial bulge deliberately. By choosing the right altitude and inclination, engineers can set a satellite into an orbit whose nodal regression exactly matches the rate at which Earth moves around the Sun, about 1 degree per day. The result is a satellite that always crosses the equator at the same local solar time. It sees every part of the Earth in the same lighting conditions on every pass. The Sun is always at the same angle in its field of view. This is enormously useful for environmental monitoring because it makes it easy to compare images taken days or months apart without worrying about different shadows or lighting. It's used for tracking sea ice, monitoring deforestation, watching crop growth, detecting wildfires, all the applications where you need consistent imaging conditions over long periods of time. Your daily weather forecast, your satellite maps, your real-time fire detection systems, all of these rely on an orbit that exists because the Earth is not a sphere. The equatorial bulge is not a cosmetic imperfection. It is a tool, a fundamental feature of the planet's gravitational environment, exploited by engineers, relied upon by meteorologists, and monitored by climate scientists, watching it change in real time. And even that's not the deepest level of the story, because beneath the equatorial bulge, beneath the geoid, beneath all the surface-level weirdness of the planet's shape, is something stranger still. The Earth, seen from the inside, is not even a consistent solid. It's a layered, dynamic, partially molten system of enormously varying densities. And the shape of the Earth, the true shape, the gravitational shape, the geoid, is determined not by the surface we can see, but by everything beneath it. By the rocky crust, and the solid mantle, and the liquid outer core, and the solid inner core at the very center of the planet. And those layers are not uniform, not by a long way. Chapter 4, What's Inside Matters, the lumpy interior. Let's go down, not literally. No drill has ever penetrated more than 12 kilometers into the Earth's crust. The Kola superdeep borehole in Russia, the deepest human-made hole ever drilled, reached 12.2 kilometers before the heat and pressure became insurmountable. And even that is less than 0.2% of the way to the Earth's center. We have never directly sampled the deep Earth, and yet we know what's down there, not from drilling, from listening. Seismology is the science of reading the Earth's interior through the vibrations that earthquakes send through it. When a large earthquake occurs anywhere on the planet, it sends seismic waves radiating outward in every direction, including downward, through the body of the Earth itself. Different types of seismic waves travel at different speeds through different materials. Some types can pass through liquid, others can't. Some are refracted, bent, as they pass through regions of different density by placing seismometers at stations all around the globe and recording how these waves arrive. Geophysicists can reconstruct, with remarkable resolution, the three-dimensional structure of the planet's interior. It's like doing an ultrasound on the planet, using earthquakes as the pulse. And what seismology has revealed is a planet that is far more structurally varied, far more internally complex than any textbook diagram suggests. Let's start with the basics, then push into the weird parts. The Earth has 4 main layers. The crust, the thin, rocky shell we live on, ranging from about 5 kilometers thick under the oceans to about 70 kilometers thick under the thickest mountain ranges. Beneath the crust, the mantle, a vast, hot, rocky layer about 2,890 kilometers thick. Beneath the mantle, the outer core, liquid iron and nickel, about 2,200 kilometers thick. And at the very center, the inner core, solid iron, about 1,220 kilometers in radius, roughly the size of the moon. That's the simple version. That's what the textbooks say. Here's what the textbooks don't say. The mantle is not uniform. In the last several decades, a technique called seismic tomography, essentially creating 3D X-ray images of the Earth's interior from thousands of earthquake observations, has revealed that the mantle is riddled with structures. Hot blobs and cold slabs, upwellings and downwellings, vast columns of superheated rock rising from the boundary with the core, eventually erupting through the surface as the volcanoes that form oceanic island chains like Hawaii. Ancient slabs of ocean crust that were subducted tens or hundreds of millions of years ago, now sitting still and cold at depths of 600, 900, even 2,700 kilometers. A geological archive of plate movements going back to the early Earth. Some of these structures are enormous. There are 2 continent-sized blobs, anomalously dense material sitting at the base of the mantle, one beneath Africa and one beneath the Pacific Ocean. They're called large, low shear velocity provinces, which is geophysicist for huge, weird blobs we don't completely understand. They may be primordial, relics of the early Earth's formation, preserved by their own density for 4.5 billion years. They may be enriched with ancient oceanic crust. Their chemical composition, their exact structure, their origin, and their long-term fate are all actively debated. But what's important for our story is this. Those blobs are real, they're enormous, and they alter the gravitational field of the planet above them. Dense material, higher gravity; lighter material, lower gravity. The uneven distribution of mass in the mantle, the core, and the crust is directly responsible for the lumpy, irregular geoid we saw in the previous chapter. The shape of the Earth's surface is determined by what's hundreds of kilometers underground. Now, let's talk about the inner core, because the inner core has a shape problem of its own. For decades, the inner core was modeled as a simple sphere of solid iron, crystallized from the cooling of the liquid outer core over billions of years. Spherical, uniform, boring, a ball of solid metal in the middle of the planet. Then seismologists started noticing something strange. Seismic waves passing through the inner core don't behave the same in all directions. They travel faster when moving along the Earth's rotation axis, from pole to pole, than when moving through the equatorial plane. This anisotropy, This directional difference in how the core transmits seismic waves indicates that the iron crystals in the inner core are not randomly oriented. They are aligned, preferentially arranged along the polar axis, as if the entire inner core grew under some directional force that pushed the crystals to align in one direction. What force? Almost certainly the Earth's magnetic field, which runs along the rotational axis. As the inner core grew, the magnetic field organized the crystalline structure of the iron, imprinting its own geometry on the planet's heart. But that's not the strange part. The strange part is what happened when seismologists looked even more carefully. Around 2002, seismologists discovered that the inner core appears to have an innermost inner core, a distinct region at the very center, perhaps 600 kilometers across, that is seismically different from the outer part of the inner core. The crystals in this innermost region appear to be aligned differently, oriented east-west rather than north-south, at roughly right angles to the orientation of the outer inner core. Why? Nobody knows for certain. The prevailing theory is that the innermost inner core formed first, during an early period of Earth's history, when conditions were different, perhaps when the magnetic field had a different orientation. As the planet evolved, the field changed, and subsequent growth of the inner core recorded the new orientation, while the old interior preserved the original one. The inner core has a memory. Its internal structure is a seismic fossil of the ancient Earth, the record of the magnetic field at the center of the planet, preserved in crystal alignment for billions of years. And it gets stranger. More recent research has suggested the inner core may be rotating independently of the rest of the Earth, spinning at a slightly different rate, on a slightly different axis, slowly wobbling through its own orientation cycle over decades. If this is confirmed, the solid center of the planet is not fixed. It moves. It wobbles relative to us on the surface. In 2023, a study published in Nature Geoscience suggested that the inner core may have recently slowed its super-rotation, the slight additional rotation relative to the rest of the planet, and may even have reversed direction. Not the Earth's rotation, just the inner core's relative to the surface. A giant ball of iron the size of the moon, spinning independently inside the planet, possibly changing its rate on a multi-decade timescale. The center of the Earth is in motion that we don't fully understand yet. And all of this, the blobs in the mantle, the ancient subducted slabs, the crystalline inner core, the innermost inner core, the possible rotation, all of it influences the gravitational field, and therefore the geoid, and therefore the true shape of the Earth. The shape of the planet is not just about its surface, it's about everything, all the way down to a spinning iron sphere the size of the moon at the very center. Chapter 5. The Satellite Revolution. How we finally saw the truth. Here's the thing about all of this knowledge. The geoid, the mantle blobs, the equatorial bulge and its changes, the seismic structure of the inner core. Most of it was either unknown or very poorly constrained until extremely recently. The fundamental revolution in our understanding of the Earth's shape happened not from the ground, but from space. And it happened in roughly the last 30 years. Before satellite geodesy, before we could put instruments in orbit and precisely measure the gravitational field from above. Our understanding of the geoid was crude and incomplete. We could measure gravity on the surface using gravimeters, and we could average those measurements to construct a rough picture of the geoid. But the surface is largely covered by ocean, and you can't sail a research ship to every point on the ocean and drop a gravimeter overboard. The data was sparse. The model was full of gaps. Then came the satellites. The key insight is simple in principle and revolutionary in practice. A satellite in low Earth orbit is in free fall around the planet. It's always falling toward the Earth, but also always moving fast enough sideways that it keeps missing. The precise orbit it follows is determined entirely by the gravitational field it's moving through. If the gravitational field is stronger in one spot, the satellite speeds up slightly. If it's weaker, it slows slightly. The satellite's trajectory is, in a very precise sense, a direct readout of the gravitational field. If you can measure the satellite's position and velocity with sufficient precision, you can invert that information to reconstruct the gravitational field, and therefore the geoid, everywhere the satellite passes. The problem is sufficient precision. In the 1970s and 1980s, measuring a satellite's orbit with the precision needed to detect subtle gravitational variations was essentially impossible. GPS hadn't been invented. Laser ranging was in its infancy. The data was too noisy. Then GPS changed everything. Suddenly, it was possible to track satellites to centimeter-level accuracy, and geodesists realized they could use constellations of GPS receivers on the ground, on ships, on other satellites, to track the precise orbits of dedicated gravity mapping missions with extraordinary precision. The first major mission to exploit this was CHAMP, Challenging Mini-Satellite Payload, launched in 2000. CHAMP was a German satellite that made continuous GPS measurements as it orbited, building a global map of gravitational variations, better than anything before it. Then came GRACE. GRACE, the Gravity Recovery and Climate Experiment, launched in 2002, and it changed everything. GRACE didn't just use GPS tracking from the ground. GRACE consisted of 2 satellites flying in formation, about 220 kilometers apart, in the same polar orbit. And the key instrument was a microwave ranging system that continuously measured the distance between the 2 satellites to an accuracy of about 1 micron, 1/1,000,000th of a meter, a distance shorter than a bacterium. The idea was this. As the lead satellite in the pair approached a region of stronger gravity, it would accelerate slightly before the trailing satellite did. The gap between them would momentarily increase. Then, as the lead satellite passed the dense region, gravity would pull it back, and the trailing satellite would begin accelerating. The gap would shrink. Then the trailing satellite would pass the region, the gap would fluctuate again, and so on. By continuously measuring these minute changes in the distance between 2 satellites, GRACE was essentially using space itself as a ruler, reading the gravitational field with unprecedented precision over the entire globe every 30 days. What GRACE saw was transformative, not just a better map of the static geoid, though it produced one, far better than anything before, but a dynamic map, a monthly map, a record of how the gravitational field of the Earth changes over time. And what changed? Water. The single largest signal in the GRACE data, the most dramatic month-to-month variation in Earth's gravitational field, was the movement of water. Every year, The monsoon season in South Asia brings enormous quantities of water inland, soaking into the ground, filling reservoirs, raising river levels. Grace could see this from space. It could see the gravitational signal of the monsoon, the subtle increase in mass across the Indian subcontinent as billions of tons of water arrived with the rains, and the decrease as it drained away again. Grace could see the annual snowfall on the Tibetan Plateau. It could see groundwater depletion in the California Central Valley as irrigation pumped water out of aquifers faster than it could recharge. It could see the Greenland ice sheet losing mass, not the speculative estimate, but the measured reality in billions of tons per year from satellite data that left no room for debate. Grace saw the 2004 Indian Ocean tsunami, the massive earthquake that killed 230,000 people and triggered a series of waves that devastated coastlines across the Indian Ocean. The earthquake was so powerful that it shifted enough mass in the Earth's crust to leave a detectable signal in Grace's gravitational maps. The planet itself registered the earthquake as a gravitational event, and the satellite caught it. Grace's successor mission, Grace-FO, the follow-on, launched in 2018 and continues today, building a now multi-decade record of changes in Earth's mass distribution. The data is extraordinary. Greenland is losing ice faster than the 2002 Grace mission's average. Glaciers in the Himalayas, the Andes, the Alps are all showing up as gravitational absences. Regions where the satellite's instruments register less pull because the mass that used to be there as ice is now in the ocean. Simultaneously, the GO-CE mission, the one that produced the detailed geoid map we talked about earlier, flew from 2009 to 2013, mapping the static geoid at a resolution of about 100 kilometers. Good enough to see individual geological structures, to distinguish the gravitational effect of mountain ranges, subduction zones, mid-ocean ridges, sedimentary basins. Put together, these missions have given us something we've never had before: a precise, dynamic, three-dimensional map of the Earth's gravitational field, updated regularly, available to any researcher in the world. And what that map shows is a planet in constant motion, a planet whose shape changes with the seasons, with the rainfall, with the tidal cycles, with the slow creep of ice into the ocean, with the even slower but inexorable movement of tectonic plates. The Earth is not sitting still. It is reshaping itself, continuously, driven by forces from both inside and outside. The interior heat driving mantle convection and plate tectonics, the exterior climate driving the redistribution of water and ice. The satellite data has also confirmed something that scientists suspected but couldn't prove until the measurements were precise enough: post-glacial rebound. During the last ice age, which peaked about 20,000 years ago, enormous ice sheets, some of them 3 to 4 kilometers thick, covered much of North America, Northern Europe, and Antarctica. The weight of that ice pressed down on the continents beneath it, slowly deforming the crust and pushing it down into the mantle. When the ice melted, over roughly the next 10,000 years, the weight was removed. But the crust didn't spring back instantly. The mantle beneath it is viscous. It flows, but slowly. And so the crust has been slowly, continuously rebounding upward ever since. In Scandinavia, the land is still rising at up to 10 millimeters per year. In parts of Canada, similarly, the crust is still catching up to an ice sheet that melted 8,000 years ago. This means that the shape of the Earth, the actual geometric shape of its surface, is still responding to an event from 8,000 years ago. The planet has not yet fully recovered from the last ice age. The rebound is measurable. GPS receivers in Scandinavia track it year by year. GRACE satellites see the change in mass distribution as the crust rises. The Earth's shape is carrying the memory of past ice ages. The surface you're standing on is still moving because of an ice sheet that melted before the first cities were built. History written in elevation. But post-glacial rebound is not just a geological curiosity. It is actively complicating our measurements of sea level rise, and therefore our ability to predict which coastal cities will flood. Here's the problem. When we measure sea level, we typically do it with tide gauges, instruments bolted to coastlines that record the height of the ocean's surface over time. And the data from tide gauges in Scandinavia and northern Canada shows something apparently paradoxical. Sea level in those regions is falling, not rising. Falling. Even as global warming pumps more water into the oceans, and global mean sea level rises at about 3.7 millimeters per year, tide gauges in parts of Sweden and Finland are recording the sea going down relative to the land, because the land is rising faster than the ocean. Post-glacial rebound in Scandinavia reaches up to 10 millimeters of land rise per year in the most active regions, outpacing the global sea level rise by nearly 3-to-1. Relative to the rising land, the ocean is actually getting lower. Stockholm, in a very literal and measurable sense, is getting higher above the sea every single year. In the shallowest parts of the Gulf of Bothnia, sea floor that was submerged a few centuries ago is now dry land. New islands have appeared in historical times. Old harbor towns have had to move their docks progressively seaward as the water retreated from the rising coast. This makes perfect sense once you understand it. But it creates a serious scientific problem. Tide gauge records, the primary tool we've used to monitor sea level for over a century, are measuring two things simultaneously: the rise of the global ocean and the rise or fall of the specific piece of land the gauge is bolted to. Those two signals are completely entangled in the raw data. To extract the true global sea level signal, you have to subtract out the local land motion at every gauge location. And calculating that land motion, the post-glacial rebound rate at each tide gauge, requires a sophisticated model of the Earth's interior. Specifically, it requires knowing the viscosity of the mantle beneath each location, how easily the rock flows, how quickly it responds to the removal of ice loads, how far the rebound has progressed in the 10,000 years since the ice melted, the shape of the Earth's interior, the viscosity structure of the mantle, the density distribution of the crust, is not something we can measure directly. We infer it from seismic data, from geodetic observations, from the rebound rates themselves. The model is good, but it is not perfect, and the imperfection in our model of the Earth's interior translates directly into uncertainty in our sea level measurements, which translates into uncertainty in our flood projections, which translates into uncertainty in how we plan and fund coastal defenses for cities like Miami, Jakarta, Amsterdam, and Shanghai. The shape of the deep Earth has direct consequences for decisions being made right now about human infrastructure and human lives. It is not an abstract scientific concern. GRACE-FO, the ongoing gravity satellite mission, is helping. By directly measuring the change in mass distribution at tide gauge locations, watching the land actually rise as a gravitational signal, it's possible to cross-check the rebound models against real satellite data and correct the tide gauge records more accurately than ever before. The satellite isn't just telling us about the shape of the Earth in some abstract way. It is providing data that feeds directly into the sea level models that governments use to plan for the future. The satellite revolution, in other words, is not finished. It has been running for roughly 2 decades, and it continues to sharpen our picture of the planet. Every new orbit, every new month of GRACE-FO data adds another layer of precision to the GEOID map, another data point in the post-glacial rebound record, another measurement of the shifting mass of ice sheets and groundwater and monsoon rainfall. And with every improvement in precision, something new appears, something that wasn't visible at the previous resolution, a subtlety in the mantle's response, an unexpected acceleration in Greenland's ice loss, a groundwater aquifer depleting faster than the models predicted, a glacial rebound rate that doesn't quite match the viscosity model. The Earth is a system of systems, and we have only recently acquired the instruments sensitive enough to see it as one. There is one more consequence of the satellite revolution worth pausing on, because it reframes something most people think of as a solved problem. GPS. You use GPS every day. Your phone uses it to navigate. Aircraft use it to land. Ships use it to cross oceans. It is perhaps the most relied upon technological system in modern civilization, and most people assume it simply works. That you tap the map, a satellite figures out where you are, and a blue dot appears with reassuring precision. What almost nobody knows is that GPS accuracy depends critically on knowing the shape of the Earth. When a GPS receiver calculates your position, it does so by triangulating signals from multiple satellites simultaneously. Each satellite broadcasts its own precise position and the exact time its signal was sent. Your receiver measures the tiny differences in arrival time from multiple satellites, and from those differences, it calculates where you must be in 3-dimensional space. But 3-dimensional space has to be measured relative to something, and that something, the reference surface against which every GPS coordinate is defined, is a mathematical model of the Earth's shape called the WGS-84 ellipsoid, the World Geodetic System 1984. A precisely defined oblate spheroid with a specified equatorial radius, a specified polar flattening, a specified rotational rate, and a specified gravitational parameter. Every GPS coordinate in the world is expressed relative to that ellipsoid. Every map, every navigation system, every surveyed property boundary, every construction project, every automated vehicle driving itself down a road. The WGS-84 ellipsoid is not the GeoID. It's a smooth mathematical approximation. And the difference between WGS-84 and the actual GeoID, which varies by up to 100 meters at different points on the globe, is stored in a separate data file called a GeoID model, which GPS receivers and surveying software use to convert between the ellipsoidal height and the orthometric height, what we call elevation above sea level. In practice, This means that every time your navigation app tells you that you're at a certain elevation, it has silently consulted a geoid model, a model of the Earth's lumpy gravitational surface, to give you a number that corresponds to what sea level would actually be at your location. The GeoID is not visible to you. You just see the elevation, but without it, the number would be meaningless for any practical purpose involving water drainage, flood risk, construction foundations, or the routing of any fluid from one place to another. The GeoID is infrastructure. Invisible, foundational infrastructure, more fundamental than any road or pipe or cable. And it is built from measurements of the Earth's gravitational field, gathered by satellites orbiting hundreds of kilometers above your head. And every few years, as the GeoID models are refined with better satellite data, the official numbers change. Slightly. By centimeters in most places. By a little more in regions where the previous data was sparse. When the United States updates its official vertical datum, the GeoID model underlying all American elevation references, every map, every flood zone designation, every elevation certificate for every insured building in the country is technically out of date. The next major update is already in progress. The National Geodetic Survey is developing a new GeoID model, NAPGD 2022, using years of satellite gravity data, airborne gravity surveys, and terrestrial measurements. When it's adopted, benchmark elevations across the country will shift, in some areas by less than a centimeter, in others by a meter or more. A meter. Flood zones drawn on the current datum will need to be redrawn. Properties on the boundary of flood designation may find themselves reclassified. Insurance rates may change. Infrastructure built to current elevation standards may need to be reassessed. All because we got a better measurement of the shape of the Earth. This is what makes geodesy, the science of the moor, Earth's shape and gravity field, so much more consequential than it sounds. It's not an academic exercise. It underpins GPS, sea level measurement, flood prediction, infrastructure planning, climate monitoring, and satellite operations. The shape of the Earth is not a settled question filed away in the solved problems cabinet of science. It is an active, ongoing field of measurement and discovery, with immediate practical consequences that touch nearly every aspect of modern civilized life. And we've only scratched the surface, because everything we've talked about so far, the oblate spheroid, the geoid, the equatorial bulge, the interior structure, the satellite revolution, has treated the Earth as something that changes slowly, geologically, on timescales of years, decades, millennia. But the Earth's shape also changes fast enough that we can watch it happen in real time, with instruments sensitive enough to catch the planet mid-motion. The Earth wobbles, and the wobble is one of the strangest, most consequential, and most recently illuminated aspects of the planet's shape, which is exactly where Part 2 begins. Chapter 6. The Wobble, Earth's Changing Axis. Here's something that should unsettle you. The North Pole is moving, not the magnetic North Pole. That one moves constantly, and most people have at least vaguely heard about it. I mean the geographic North Pole, the rotational pole, the actual axis around which the Earth spins. The point that defines north on every map, every compass bearing, every coordinate system ever devised. That point is not fixed, it wanders. slowly, erratically, in a rough spiral across the Arctic, drifting a few meters every year, shifting its average position over decades in response to changes in how mass is distributed across the planet. And in the last 20 years, it has accelerated. The direction of polar drift has changed. And the cause, researchers have confirmed, is us. Let's back up and build this properly. Because the wobble of the Earth is one of those topics that sounds like it should be frightening, and in some ways it is, but is also one of the most elegant demonstrations of physics operating at planetary scale. The Earth spins on an axis. That axis is tilted about 23.5 degrees relative to the plane of Earth's orbit around the Sun. That tilt is what gives us seasons. But the axis itself is not perfectly stable. It wobbles in several distinct ways on several distinct timescales for several distinct reasons. The first and most famous wobble is precession. The Earth's axis slowly traces a circle in space, like the wobble of a gyroscope that's been given a push. One full precession cycle takes about 26,000 years. Right now, the Earth's axis points toward Polaris, the North Star. In 13,000 years, it will point toward a star called Vega. In 26,000 years, it will be back to Polaris. Ancient astronomers noticed this. It was documented by the Greek astronomer Hipparchus around 127 BC, though the full explanation had to wait for Newton. The cause of precession is the gravitational pull of the Moon and the Sun on the Earth's equatorial bulge. Remember that bulge? The 21 kilometers of extra equatorial girth caused by rotation? The Moon and Sun don't just pull on the Earth's center of mass. They also exert a torque on the bulge, a twisting force that slowly rotates the orientation of the Earth's spin axis. It's the same physics that makes a spinning top precess rather than simply falling over when gravity acts on it. The second wobble is nutation, a smaller, shorter wobble superimposed on the precession. Nutation is caused by the varying gravitational pull of the Moon as it moves through its orbit, which is itself tilted and elliptical. The main nutation cycle is about 18.6 years. It's a subtle nodding motion of the axis, measurable only with precise instruments. Then there's the Chandler wobble. The Chandler wobble is different from precession and nutation. It's not caused by external gravitational forces. It's caused by the fact that the Earth is not a perfect sphere, and therefore its rotation axis and its geometric axis don't quite coincide. Here's the physics. For a perfectly spherical body, the rotation axis and the geometric axis are always the same. They can't be anything other than the same, because the sphere looks identical in every direction. But for an oblate spheroid, or for any body with an uneven mass distribution, the situation is more complicated. The axis around which the body actually spins can be slightly offset from the axis of maximum moment of inertia. And when this happens, the body wobbles. The rotation axis traces a small circle around the symmetry axis. For the Earth, this wobble has a period of about 433 days, just over 14 months, and an amplitude of about 3 to 6 meters at the poles. The geographic pole traces a rough circle, a few meters across, over that 14-month period. When Seth Carlo Chandler first measured this wobble in 1891, he was puzzled by something. The wobble should, in theory, damp out over time. The Earth should gradually dissipate the energy of the wobble, and settle into a stable spin. But it doesn't. It keeps going. Something must be continuously re-exciting it, pumping energy back into the wobble to keep it going. What is that something? For over a century, this was an open question. The answer, when it finally came together in the early 2000s, turned out to be fluid. Specifically, the movement of ocean water and atmospheric pressure fluctuations. The ocean is not static. It sloshes. Water piles up in some regions, drains from others, redistributes with the seasons, and with long-term climate patterns. Atmospheric pressure varies across the planet, loading the crust unevenly. All of these fluid redistributions slightly shift the Earth's mass distribution, which tweaks the offset between the rotation axis and the symmetry axis, which perpetually re-excites the Chandler wobble. The ocean is keeping the Earth wobbling. The air is keeping the Earth wobbling. Fluid dynamics at the surface of the planet is maintaining a 433-day oscillation in the position of the geographic pole. Now, here's where it gets contemporary. Here's where the physics connects to the present and to us. The geographic pole doesn't just wobble on a 433-day cycle, it also drifts, a long-term secular trend in the average position of the pole, distinct from the Chandler wobble. And that drift has been measured since the late 19th century. For most of the 20th century, the pole drifted roughly toward Hudson Bay in Canada. The direction that makes sense if you know your post-glacial rebound history, because the enormous mass of the Laurentide ice sheet that covered Canada and melted starting 20,000 years ago has left a gravitational imprint, and the pole tends to drift toward regions where mass has been added or removed. But around the year 2000, something changed. The drift direction shifted. The pole, which had been drifting toward Hudson Bay, began moving in a new direction, now toward Greenland, and the rate of drift increased. In 2016, a team of researchers published a study in Science Advances identifying the cause. 2 factors. First, the accelerating loss of ice from Greenland, which is redistributing mass from a polar region into the global ocean, is pulling the pole toward Greenland as the mass balance shifts. Second, groundwater depletion. In the 20th century, humans pumped enormous quantities of groundwater out of underground aquifers, primarily for agriculture, in mid-latitude regions. That water, extracted from underground, eventually made its way to the ocean. The redistribution of that mass, from underground aquifers at mid-latitudes to the global ocean, also contributes to the shift in polar drift. Human water use moved the poles. Human ice melt is continuing to move them and accelerating the movement. This is not a metaphor. The coordinates of the geographic North Pole are changing measurably year by year because of human activity. GPS receivers, satellite reference frames, and global navigation systems all have to account for this. The International Earth Rotation and Reference Systems Service, the organization responsible for maintaining the global reference frame that GPS depends on, monitors the pole's position continuously and publishes updates. Every few years, when the accumulated drift is large enough to matter, the reference frame has to be updated. Navigation depends on knowing where the pole is, and the pole is moving because of climate change and agricultural groundwater use. The wobble is not abstract. It is not a curiosity for specialists. It is an active, human-caused, GPS-relevant, climate-linked drift in the orientation of the planet itself. But there is one more layer to the wobble story, and it may be the most surprising of all. The 23.5-degree tilt of the Earth's axis, the obliquity, is also not fixed on long timescales. Over cycles of approximately 41,000 years, the tilt varies between about 22.1 and 24.5 degrees. Right now, at 23.44 degrees, we are in the middle of that range, and the tilt is slowly decreasing. This variation in tilt is one of the 3 Milankovitch cycles, orbital and rotational parameters that modulate how much sunlight reaches different parts of the Earth at different times of year, and which are believed to be the primary pacemaker of the ice ages. The wobble of the axis, on timescales from 14 months to 41,000 years, has shaped the climate of the entire Cenozoic era. The ice ages, the interglacials, the expansion and retreat of the polar ice caps, all of it choreographed in significant part by the way the Earth wobbles as it spins. The shape of the Earth drives the wobble. The wobble drives the climate. The climate drives the shape. It's a loop, a deeply interconnected, continuously evolving loop, and we are now a variable inside it. But let's sit with the Milankovitch cycles for a moment, because they deserve more than a passing mention, because the implications of orbital wobble for human history are staggering in a way that doesn't get nearly enough attention. The 3 Milankovitch cycles, obliquity, precession, and eccentricity, operate on timescales of 41,000 years, 26,000 years, and roughly 100,000 years, respectively. Eccentricity is the third one we haven't covered. It describes how elliptical or circular the Earth's orbit around the Sun is at any given time. When the orbit is more elliptical, the difference in solar energy received at perihelion, Earth's closest approach to the Sun, versus aphelion, its farthest, is larger. When the orbit is nearly circular, the difference is smaller. None of these cycles individually is enough to trigger an ice age. But when they align, when the orbital geometry conspires to reduce summer solar insolation at high northern latitudes, snow that falls in summer doesn't fully melt. It accumulates year on year. The ice sheet grows. Its white surface reflects more sunlight back into space, cooling the planet further. Atmospheric CO2 drops as the cold ocean absorbs more of it. The cooling accelerates. An ice age begins. This is the story of the last 2 million years. Glacial and interglacial periods cycling in rough time with the Milankovitch rhythms, advancing and retreating ice sheets that have repeatedly buried much of North America and Europe under kilometers of ice, and then melting back, and then advancing again. The Sahara has been green and wet during some interglacials. Satellite imagery reveals ancient river valleys beneath the dunes, carved by rivers that haven't flowed for thousands of years. The Amazon basin has contracted and expanded. Sea levels have risen and fallen by 120 meters between glacial maximum and interglacial peak. All of this driven by wobble, by the slow orbital variations of a non-spherical planet orbiting a star. Here is the part that should genuinely stop you in your tracks. We are currently in an interglacial, the Holocene, which began about 11,700 years ago when the last ice age ended. And the Milankovitch calculations suggest that, under natural conditions, the next glacial period should begin somewhere between 1,500 and 50,000 years from now. The uncertainty is large because the cycles interact in complex ways. Some researchers have argued that the current interglacial is unusually long, possibly extended by early human agriculture, which added CO2 and methane to the atmosphere thousands of years before the Industrial Revolution. In other words, human civilization may have already altered one Milankovitch cycle's outcome. The ice age that should have been beginning may have been delayed by 10,000 years of human land use and farming. And now, with industrial greenhouse gas emissions driving CO2 to levels not seen in at least 3 million years, the question of whether the next ice age will arrive on schedule or be indefinitely postponed, replaced by a prolonged warm period with dramatically different geography, is one of the genuinely open questions in long-term Earth system science. The wobble of the Earth's axis is competing with the composition of its atmosphere. Shape versus chemistry. Orbital mechanics versus human industry. Two planetary forces operating on different timescales, pulling the climate in opposite directions. That is the world we have built. That is the planetary system we now inhabit and influence. And understanding it, all the way down to why the axis wobbles and how it interacts with solar insolation and ice sheet dynamics and ocean circulation, requires knowing the shape of the Earth. Not just the rough shape, the precise shape, the dynamic shape, the shape that satellites are measuring right now, that seismologists are probing with earthquake waves, that GPS receivers are tracking at millimeter precision across every continent. The shape of the Earth is not a number to be memorized. It is a question to be continuously answered. Chapter 7: The View from Space. What Earth actually looks like. Let's step back and try to see the whole thing at once. If you were an alien astronomer approaching the solar system for the first time, and you turned your instruments toward the third planet, what would you see? From a distance, you'd see a blue sphere, mostly ocean, white swirls of cloud, patches of brown and green where the continents break the surface. It would look from far enough away like the photographs you've seen 1,000 times. The blue marble, the pale blue dot, the Apollo images of Earth hanging in the black. From that distance, it looks like a sphere, a beautiful, perfect sphere. Get closer, get precise instruments, start measuring, and what you'd find is that the Earth is, in fact, an oblate spheroid, measurably wider at the equator than at the poles, exactly as Newton predicted. At the resolution of a casual observation, it still looks round, but the numbers are clear. Get closer still. Get an instrument sensitive to variations in the gravitational field, the way Gaussian was. And now you see something very different. The geoid, the true gravitational shape, emerges like a face appearing in a blurred photograph as the resolution increases. The Indian Ocean dent, the bulge over New Guinea, the complex topography of the gravitational field, responding to every mountain range, every dense slab of subducted oceanic crust, every blob of anomalous material in the deep mantle. The planet stops looking like a sphere and starts looking like a lumpy, irregular, deeply asymmetric object. Rotationally almost symmetric, the equatorial bulge is consistent all the way around, but in every other respect, irregular. The gravitational field is higher over the Andes than over the mid-ocean ridges. It dips over the ancient cratons. the old, stable cores of continents. It surges over the subduction zones, where dense oceanic plates plunge downward. Now watch it over time. Watch a year pass. In the northern winter, mass moves from the oceans to the continents as snow accumulates. The equatorial regions lose a tiny fraction of their water to polar snowfall. The gravitational field shifts. The geoid breathes. In northern summer, the snow melts. The mass returns to the oceans. The geoid shifts back. Watch a decade pass. The Greenland ice sheet loses billions of tons of mass per year, decade after decade. The gravitational signature of Greenland weakens. The global ocean gains mass. The geoid responds. The equatorial ocean surface rises fractionally. The polar regions around Greenland register a gravitational decrease detectable from orbit. Watch a century pass. Post-glacial rebound continues. Scandinavia rises. The Hudson Bay region rises. The crust of Antarctica, beneath its remaining ice sheet, is also rising slightly as the ice at its edges thins. Simultaneously, as sea level rises and the ocean loads the continental shelves with additional water mass, coastal regions are pressed down very slightly under the extra weight. The entire planet is in motion, vertically, laterally, rotationally. The surface you are standing on is not still. It is rising or falling at millimeters per year, driven by forces operating at depths of hundreds of kilometers, responding to events that happened thousands of years ago and to activities happening right now. There is a concept in geodesy called the dynamic Earth, the recognition that the planet's shape is not a fixed parameter, but a time-varying quantity that must be continuously monitored and updated. This is why the International Terrestrial Reference Frame, the coordinate system underlying GPS and all global navigation, is not a static set of numbers, but a continuously updated model. The position of every reference point on the Earth's surface changes year by year. GPS ground stations that anchor the reference frame drift as tectonic plates move. The entire Australian continent moves northward at about 7 centimeters per year. GPS coordinates fixed to the Australian plate become slightly wrong every year, so slightly that it doesn't matter for everyday navigation, but enough to matter for precise scientific measurement and for the agricultural and mining applications that operate at centimeter accuracy. Australia had to update its official coordinate system in 2020 because the continental drift had moved the landmass nearly 2 meters from where the old coordinate system placed it. The continent moved. The maps had to catch up. This is the Earth we actually live on. Not the static globe of the classroom. Not the smooth mathematical ellipsoid of the textbook. A dynamic, heaving, drifting, wobbling, breathing, gravitationally lumpy object that is continuously reshaping itself in response to its interior dynamics, its climate, its orbital parameters, and now, in measurable ways, the activities of a technological civilization that has been present for the blink of a geological eye. The continent moved. The maps had to catch up. This is the Earth we actually live on. Not the static globe of the classroom. Not the smooth mathematical ellipsoid of the textbook. A dynamic, heaving, drifting, wobbling, breathing, gravitationally lumpy object that is continuously reshaping itself in response to its interior dynamics, its climate, its orbital parameters, and now, in measurable ways, the activities of a technological civilization that has been present for the blink of a geological eye. And here is something that puts all of this into sharp relief. Something that rarely gets mentioned in discussions of Earth's shape, but that I think is one of the most illuminating comparisons in planetary science. Earth is not the only planet whose shape we've measured. We've sent spacecraft to Mars, Venus, Mercury, the Moon, Jupiter, Saturn, and beyond. We've measured their gravity fields, mapped their surfaces with radar and laser altimetry, and in several cases built detailed GeoID equivalent models of their gravitational shapes. And what those comparisons reveal is that Earth's shape, its particular brand of lumpiness, its specific wobble, its exact degree of polar flattening, is deeply, intimately connected to the fact that it is alive. Not biologically alive in this context. Geologically alive. Consider Mars. Mars is also an oblate spheroid. It bulges at its equator, as any rotating planet does. But Mars's equatorial bulge is proportionally larger than Earth's, partly because Mars rotates at a very similar rate to Earth, but is smaller, and partly because Mars cooled faster and its interior solidified more completely, locking in a larger fossil bulge from a period when it was rotating faster. The Martian geoid is also lumpy, dramatically so, dominated by the gravitational signature of the Tharsis Plateau, an enormous volcanic highland on one side of the planet so massive that it has tilted Mars's entire crust relative to its rotation axis. Tharsis is so heavy that it pulled the crust of Mars around until Tharsis sat near the equator, minimizing the planet's rotational energy. The entire Martian crust reoriented itself around one enormous pile of volcanic rock. But here's what Mars doesn't have: an active interior driving continuous change. Mars's interior has largely solidified. Its magnetic field died billions of years ago when the core cooled enough that convection stopped. Its tectonic plates, if it ever had them in the form Earth does, ceased moving. Volcanoes on Mars are dormant or extinct. The Martian geoid is, in the current era, essentially static. It doesn't breathe with the seasons in any meaningful gravitational sense. It doesn't rebound from ice ages. It doesn't respond to the redistribution of water because there's no liquid water to redistribute. The shape of Mars is a fossil, the frozen record of a geologically active past, preserved in the cold and the silence of a dead interior. Earth's shape, by contrast, is a living document. It's being written right now, continuously, by plate tectonics, mantle convection, the water cycle, the ice cycle, the carbon cycle, and now by human activity. Every subduction zone, dragging dense oceanic crust into the mantle, slightly alters the gravitational field above it. Every volcanic eruption adds mass to one part of the surface. Every glacier that retreats removes a load from the crust, which then slowly rebounds. Every aquifer pumped dry shifts mass from underground to the ocean. The dynamism of Earth's shape is a direct consequence of Earth's dynamism as a planet. The fact that we have a liquid outer core generating a magnetic field means the planet has heat to lose, which means mantle convection, which means plate tectonics, which means the continuous recycling of the crust, which means mountain building and erosion, and the carbon cycle that keeps the climate stable enough for complex life. The lumpiness of the geoid is not a flaw in the planet's design. It is the signature of a planet that is alive in every sense of the word. A planet whose interior has not frozen, whose surface is not static, whose shape is not fixed. Saturn, for comparison, is the most oblate planet in the solar system. So oblate that you can see it with the naked eye. Its equatorial radius is about 10% larger than its polar radius compared to Earth's 0.3%. Saturn rotates once every 10.5 hours, that extreme speed flinging its gaseous body dramatically outward at the equator. But Saturn's oblate shape, dramatic as it is simple. It's what you'd expect from a rapidly rotating ball of gas. There are no tectonic plates to complicate the picture, no post-glacial rebound, no graceful satellite catching the gravitational signature of a monsoon season. Earth sits in a fascinating middle ground, not as simple as a gas giant's smooth oblateness, not as static as Mars's frozen fossil shape. Dynamic, layered, complex, responsive, and because of all those qualities, habitable. The shape of Earth is a measure of its aliveness. Now let me show you what this planet actually looks like when you remove all the water and atmosphere and look at the raw gravitational shape, the geoid, rendered as a three-dimensional surface. Because when ESA released the Gosia geoid visualization in 2011, reactions ranged from scientific excitement to something closer to cognitive dissonance. People who expected to see a sphere, or at least a slightly flattened sphere, were confronted with something that looked frankly alien. The geoid, rendered with its departures from a reference. Ellipsoid exaggerated by a factor of about 10,000 to make them visible, looks like a lopsided, deeply dented, asymmetrically lumpy object. The Indian Ocean low creates a dramatic depression, like someone pressed a thumb into the southern side of the planet. The Pacific region sits higher. The area around Iceland and the North Atlantic is elevated. The area near Antarctica shows complex structure. It doesn't look like a planet. It looks like a misshapen asteroid. And yet, this is the critical point. Those departures from a smooth ellipsoid are at most about 100 meters over a planetary radius of 6,371 kilometers. As a fraction, that's less than 0.002%. The geoid, despite its dramatic appearance in exaggerated visualizations, is extraordinarily close to a smooth oblate spheroid. If you made a scale model of the Earth the size of a billiard ball, it would be smoother than the actual billiard ball, which has surface irregularities that, at Earth scale, would be taller than Everest. The Earth is lumpy by the standards of geophysics. By the standards of everyday geometry, it is almost perfectly round. Both of these statements are true simultaneously, and understanding why both are true and why both matter is the whole point. Chapter 8: New Discoveries and Open Questions. Here's something that gets lost in popular science communication about the Earth. We talk about the planet as if it's known, mapped, understood, a solved problem beneath our feet. It isn't. The last 10 years have produced discoveries about the shape and structure of the Earth that would have been impossible to make even 20 years ago, and several of them have either overturned existing models or created new mysteries that remain genuinely open. Let's go through them. The anomalous low under the Indian Ocean. We touched on this in Chapter 2. The Indian Ocean geoid low, the 106-meter depression in the gravitational field south of India, was unexplained for decades. In 2023, researchers from the Indian Institute of Science proposed that it's caused by the remnants of the ancient Tethys seafloor, subducted into the mantle as India collided with Asia. Low-density mantle plumes rising from the region around the sinking ancient crust create a zone of reduced density, which creates reduced gravity, which pulls the sea surface down. But here's what's important. This is a proposed explanation, published in 2023 based on computer modeling. It has not been definitively confirmed. The 2023 paper attracted both support and critique from the geophysics community. Alternative explanations, involving different configurations of mantle plumes or different interpretations of the ancient plate tectonic history, have also been proposed. The largest gravitational anomaly on Earth's surface does not have a universally agreed upon explanation as of this recording. The inner core's structure and rotation, we covered the innermost inner core and the evidence for inner core superrotation in Chapter 4. But this story has developed rapidly. A 2023 paper in Nature Geoscience by Yi Yang and Xiaodong Song at Peking University analyzed seismic waves passing through the inner core over several decades and concluded that the inner core's superrotation, its slight spin relative to the rest of the planet, had slowed and possibly reversed direction around 2009 and may now be oscillating on a roughly 70-year cycle. The response from the seismology community was intense and divided. Some researchers supported the conclusion. Others argued that the seismic data could be explained by changes in the structure of the inner core's surface rather than actual rotation changes. The debate is unresolved. What's not in dispute is that the inner core is doing something complex. Whether it's rotating independently, oscillating, or evolving its crystalline structure in ways that mimic the signature of rotation, something strange is happening at the center of the planet, and we do not yet have the data to be certain what it is. Post-glacial rebound and the missing uplift. As GRACE and GPS data have accumulated, a subtle but important discrepancy has emerged. The measured rate of post-glacial rebound in some regions, particularly parts of Antarctica, doesn't match what the models predict based on the assumed viscosity of the mantle. In West Antarctica, GPS stations are recording land uplift rates that are faster than expected. Some studies suggest up to 4 times faster than the standard models predict. This could indicate that the mantle beneath West Antarctica is much less viscous than previously thought, that it flows more easily, responds more quickly to the removal of ice loads. If that's true, it has significant implications. A lower viscosity mantle means West Antarctica may be more vulnerable to a process called marine ice sheet instability, a feedback loop in which the loss of ice causes the bedrock to rise, which changes the geometry of the ice sheet's contact with the ocean, which accelerates further ice loss. If the mantle responds quickly to ice unloading, the feedback could operate on timescales of centuries rather than millennia. The shape of the Earth's interior, specifically the viscosity of the mantle under West Antarctica, may be a key variable in determining how fast global sea level rises over the next few centuries. The dynamic GeoID and GRACE-FO surprises GRACE-FO, launched in 2018 as the successor to GRACE, has been building a record that now spans more than 2 decades when combined with its predecessor's data. And the picture that's emerging is of a planet losing ice faster than the models predicted even a decade ago. Greenland's ice loss has accelerated. The rate in the 2010s was roughly twice the rate in the 2000s. The rate in the early 2020s appears to be accelerating further. The gravitational signal is unambiguous. Grace. FO is watching Greenland's mass decrease month by month, year by year, in data that requires no modeling assumptions and no interpretation. It's a direct measurement of mass change. Antarctica is more complex. The East Antarctic ice sheet, which contains enough ice to raise global sea levels by about 52 meters if it fully melted, was for a long time considered relatively stable. GRACE data suggested it might even be gaining mass in the interior, as increased precipitation in a warming atmosphere added snow to the high plateau. But the West Antarctic ice sheet and the Antarctic Peninsula are clearly losing mass, and recent data suggests the pace is increasing there too. The GRACE FO data is also revealing something unexpected about groundwater. In regions like northern India, the Middle East, the American high plains, and parts of northern China, groundwater is being depleted at rates that were known but are now starkly quantified from space. The gravitational signal of disappearing groundwater is measurable. Aquifers that took thousands of years to fill are being emptied over decades. And GRACE FO watches it happen in real time. The numbers from northern India are particularly stark. The Indo-Gangetic Plain, one of the most agriculturally productive and densely populated regions on Earth, sits above aquifers that are being drawn down at a rate of roughly 17 cubic kilometers per year. GRACE detected this not from any ground-based monitoring network, but from space, by measuring the gravitational deficit left behind as the water table dropped. The aquifer is invisible, underground, inaccessible to direct observation from the surface, but not invisible to a satellite sensitive enough to detect the difference in gravity caused by the absence of water. This is one of the most profound and least discussed applications of Earth shape science. We are running out of groundwater in some of the most food-critical regions on the planet. The primary evidence base for that claim, the data that quantifies the rate and severity of depletion with enough precision to be actionable, comes from a mission designed to measure the gravitational shape of the Earth. Food security in the 21st century is partly a gravitational measurement problem. The same GRACE FO data that tracks the Greenland ice sheet also monitors the Ogallala Aquifer beneath the American Great Plains. The vast underground reservoir that irrigates much of the corn, wheat, and soybean production, feeding a significant fraction of the world. The Ogallala is being depleted orders of magnitude faster than it recharges from rainfall and surface water infiltration. GRACE sees it draining. The gravitational signal of the high plains weakens year by year as billions of tons of water leave the aquifer and flow into irrigation channels and eventually into the atmosphere or rivers and back to the sea. What took nature tens of thousands of years to accumulate, we are extracting in decades. When the Ogallala runs critically low and at current depletion rates, large sections of it will within this century. The agricultural geography of North America will reorganize. Crop patterns will shift. Water-intensive farming will migrate. Food prices will respond. And the data underpinning every projection of when and how severely that transition will arrive comes, in significant part, from a satellite gravity mission whose primary purpose is tracking changes in the shape of the Earth. A mission measuring millimeter-scale gravitational variations from orbit is telling us when the breadbasket runs dry. That is the reach of geodesy. That is how far the consequences of understanding the Earth's shape extend into ordinary human life. Into the price of bread, the security of harvests, the future of farming communities across entire continents. The GeoWid update and the datum problem. As GeoWid models improve, a tension is emerging between the precision of our measurements and the rigidity of our infrastructure. Every country has a vertical datum, an official reference surface from which all elevations are measured. In the United States, the current official datum is called NAVD88, the North American vertical datum of 1988. It was established from a network of leveling surveys carried out over many decades, stitched together into a continent-spanning reference surface. But NAVD88 has known problems. Because it was built from ground-based surveys rather than satellite measurements, it accumulated errors over its vast extent. In some regions, the datum is off by more than a meter from what the true GeoWid would say, which means that elevation data across the country, flood maps, engineering surveys, infrastructure records, contains systematic errors of up to a meter in some places. The replacement, NAPGD2022, is designed to fix this, using satellite gravity data from GRACE and GOAC, airborne gravity surveys, and a modern GeoWid model to establish a consistent, satellite-grounded vertical reference across the continent. When it's adopted, the changes to recorded elevations will range from negligible to significant depending on location. The practical consequence is enormous. Flood insurance maps in the United States are drawn based on elevation data. Change the elevation reference, and the maps change. Properties currently outside flood zones may fall inside them. Properties currently mapped as high risk may be reclassified. Tens of millions of homeowners, hundreds of billions of dollars in property values. The operational parameters of every piece of water-related infrastructure in the country. All of it rests on the accuracy of the GeoWid model. A satellite-measured lump in the gravitational field translates into a flood insurance premium. That is the chain of consequence. That is how fundamental the shape of the Earth is to the fabric of ordinary life. Deep Earth seismic surprises. Beyond the inner core controversy, seismic tomography has continued to produce results that challenge existing models of the Earth's interior. In 2020, researchers identified what they called ultra-low velocity zones at the core mantle boundary, thin, irregular patches at the very base of the mantle where seismic waves slow down dramatically, suggesting material of unusual composition or unusually high temperature. These zones are not uniformly distributed. They cluster in specific locations, particularly beneath the large, low shear velocity provinces we discussed earlier. Their origin is unknown. Possibilities include partially molten mantle rock, ancient oceanic crust that subducted billions of years ago and pooled at the core mantle boundary, or even material that has been chemically altered by interaction with the liquid iron outer core over billions of years. In 2023, a team using a machine learning algorithm to analyze seismic data from the Pacific reported that there may be many more of these ultra-low velocity zones than previously detected, that the base of the mantle is far more topographically and compositionally complex than the earlier, lower-resolution seismic data suggested. The core mantle boundary, 2,890 kilometers beneath your feet, is not a smooth interface. It is a landscape, a geological terrain of its own, with ridges and depressions and anomalous patches of exotic material. A landscape we are only now beginning to map, and beneath even that, the outer core, the liquid iron sea that surrounds the solid inner core and generates the Earth's magnetic field through its churning convection. The outer core is almost certainly not convecting uniformly. The flow patterns are complex, three-dimensional, and driven by the solidification of the inner core at the bottom and the heat conducted through the core mantle boundary at the top. Those flow patterns determine the structure of the magnetic field, which protects the planet from the solar wind, which is one of the reasons Earth is habitable. And the magnetic field itself is not stable. It has reversed hundreds of times in Earth's history. The north and south magnetic poles swapping, the field weakening dramatically during the transition before rebuilding in the opposite orientation. The last full reversal happened about 780,000 years ago, an event recorded in the alignment of iron-rich minerals in volcanic rocks laid down at that time. The minerals, as they cooled from the lava, aligned with the prevailing magnetic field like compass needles, and then locked in place, preserving the field's orientation for geologists to read millions of years later. Right now, the magnetic field is weakening. The South Atlantic anomaly, a region of unusually weak magnetic field over the South Atlantic Ocean and parts of South America, has been growing and intensifying for decades. Satellites passing through it experience higher rates of radiation damage because the field is not strong enough in that region to deflect charged particles from the sun. The anomaly has been linked in some studies to unusual patterns in the liquid outer core beneath it, suggesting that the dynamics of the Iron Sea 3,000 kilometers underground are already beginning to shift. Whether this is the precursor to a full geomagnetic reversal, which could take thousands of years to complete, and during which the field would be significantly weakened globally, or merely a fluctuation in the field's ongoing behavior, is not yet known. What is known is that the outer core is not static, and that its dynamics are directly connected to something we depend on for our technological civilization. The magnetic shield that deflects radiation, protects the upper atmosphere, and keeps satellite electronics functioning. The shape and dynamics of the Earth's deepest interior are not remote, abstract concerns. They are connected through chains of physical consequence that span thousands of kilometers and millions of years to the conditions at the surface where we live. The shape of the Earth, all the way down to the dynamics of a churning iron sea 3,000 kilometers underground, is connected to the habitability of the surface. The shape of the Earth is the story of why life exists here. Conclusion: the planet you never knew. Let me bring you back to the classroom globe. You've probably touched one. That smooth, round, satisfying plastic sphere on its tilted stand. The countries painted in reassuring colors. The oceans a uniform blue. It sits there radiating certainty. It says, "This is the planet. Here it is. Case closed." Now you know what it's not telling you. It's not telling you that the equatorial diameter is 43 kilometers wider than the polar diameter and that the bulge is growing because ice is melting into the ocean. It's not telling you that the actual gravitational surface, the geoid, dips 106 meters below the ellipsoid south of India because the floor of a sea that closed 20 million years ago is still disturbing the mantle from 900 kilometers down. It's not telling you that the polar axis around which the globe stands is moving, drifting toward Greenland at a rate that accelerated in the year 2000 because of human ice melt and agricultural groundwater extraction. It's not telling you that the land beneath Scandinavia is still rising from the weight of an ice sheet that melted 8,000 years ago, and that this rebound is tangled into our measurements of sea level rise in ways that require satellite gravity missions to unpick. It's not telling you that at the very center of the planet, 6,371 kilometers straight down, there is a solid iron sphere the size of the moon that may be rotating independently, that contains a second, differently oriented inner sphere nested inside it, and that the crystalline structure of that innermost sphere is a fossil record of the ancient magnetic field, preserved since the early Earth. It's not telling you that the shape of the Earth is not a fixed fact, but a continuously evolving measurement, that satellites are right now, as you watch this, measuring the planet's gravitational field to micron precision, catching the monsoon as a gravitational signal, watching ice sheets lose mass in real time, monitoring the slow rebound of ancient continents, tracking the drift of the geographic pole. It's not telling you that the shape of the Earth is one of the most consequential unsolved problems in modern science, with direct implications for flood risk, sea level prediction, GPS accuracy, climate projections, and our understanding of the planet's deep interior. The globe got the rough shape right, but the rough shape is the least interesting part. What's interesting is the lumpiness, the wobble, the breathing, changing, dynamic system of systems that the planet actually is. A planet that carries its history written in gravity. The memory of ancient oceans in the geoid's dents. The memory of ice ages in the still rising Scandinavian crust. The memory of the early magnetic field in the crystal alignment of the innermost inner core. And a planet that is changing right now in ways that we are causing, and that our satellites are watching, and that our scientists are trying urgently to understand well enough to tell us what comes next. Here is something worth reflecting on before we get to the final word. The history of our understanding of the Earth's shape is, in miniature, the history of science itself. Every time we thought we had it pinned down, every time the picture looked complete and the textbooks seemed settled, reality offered a correction. The Greeks knew the Earth was round. Newton showed it wasn't quite round. 18th century surveyors showed Newton was right about the oblate spheroid. 20th century satellite geodesy showed the spheroid was only an approximation, and the real shape was the geoid. 21st century gravity missions showed the geoid was itself dynamic, changing with the seasons, with the decades, with the slow pulse of geological time and the faster pulse of human activity. At each step, the new understanding didn't invalidate the old. The Earth is still round, in the way the Greeks meant. It is still an oblate spheroid, in the way Newton predicted. It is still governed by a geoid, in the way that 19th century geodesists inferred from inconsistencies in their leveling surveys. Each new layer of understanding sits on top of the previous one, using it as a foundation and then revealing its limits. This is how all of science works. Not as a series of revolutionary breaks where everything that came before is discarded, but as a sequence of approximations, each more precise than the last, each revealing new structure that the previous approximation couldn't see. The Earth is round, then it's an oblate spheroid, then it's a geoid, then it's a dynamic geoid, then it's a dynamic geoid with a wobbling axis and a differentially rotating inner core, and a gravitational field that carries the memory of an ocean that closed 20 million years ago. At no point does it stop being interesting. At no point does it stop having more to reveal. That's the thing about reality. It doesn't have a bottom. Every time you reach what looks like the final layer of explanation, the layer below it is already waiting. The Earth's shape, examined with sufficient precision, connects to the Earth's interior, which connects to the Earth's formation, which connects to the physics of the early solar system, which connects to the physics of stellar nucleosynthesis, which connects to the Big Bang itself. The shape of the ground beneath your feet is a thread that, if you pull on it long enough and carefully enough, unravels the entire history of the universe. Most of us will never pull on it at all. We'll walk on the ground, look at the globe, and accept the sphere. But now you know the thread is there. Here is what I want you to leave with. The next time someone says the Earth is round, you can nod, in the way that you'd nod if someone said the ocean is flat. True enough from where you're standing, but carrying within it a universe of complexity that the simple statement doesn't begin to capture. The Earth is round in the way that all complicated things look simple from a distance. Get close enough, and everything gets interesting. The planet you've been standing on your whole life is stranger than you were told. Stranger than most scientists 50 years ago understood. Stranger still than we fully understand today. And that strangeness is not a problem to be solved and forgotten. It is the most important ongoing scientific question beneath your feet. Literally.